In this SBO project, Product Inspection with Little Supervision, or PILS for short, we aim to reduce the deployment cost of computer vision systems in industrial applications. A big challenge in using machine learning computer vision algorithms is the lack of sufficient labeled training data. This is especially the case in a low-volume manufacturing context, where products and environments can often change. Current techniques will augment the available data with simple translations, rotations, and contrast enhancements. These augmentations can make machine learning algorithms more robust to these types of variations. However, they are not powerful enough when none or little training data is available. In this project, we are researching how we can use computer graphics to generate synthetic images that can be used as training data for computer vision algorithms. To generate a synthetic dataset, we require a realistic scene, materials, and lighting conditions. Because we work in the context of product manufacturing, typically the CAD models are available. We can spawn a random amount of these objects in a virtual scene and use a physics engine to place them in a plausible location and orientation. The CAD models contain only information about the shape of the object, so we search a material database and assign a realistic material to the objects. We can add variations to any of the material properties to create realistic variations. Lastly, we randomly assign different environmental maps to the scene. The goal is to have a broad range of realistic environments to make training more stable against environmental changes. The fully defined scenes are then rendered using a path tracer, exploiting the hardware acceleration capabilities of the NVIDIA RTX graphics cards. The result is a dataset of photorealistic generated images accompanied with any metadata required for training a machine learning algorithm.
So here you see an example dataset rendered for a specific state tracker use case. The goal of the state tracker was that the camera can identify the tip of the screwdriver and the both ends of the wrench. This is helpful to identify what exactly an operator is performing at what time. We have rendered different variations of different screwdrivers and wrenches, but also we export its metadata. For example, a segmentation map and the 2D ground truth positions of the tips of the screwdrivers and the wrenches. After training the detection algorithms, this is the result. We achieve quite good accuracies. Overall, the tips are detected pretty well. Sometimes it fails when the tools are moving too fast and motion blur is deteriorating the detections. In the future, motion blur effects can also be inserted as a type of variation during the rendering phase.
To better be able to research how synthetic data impacts machine learning algorithms, we created together with RoboJob a dataset of real and synthetic images. For the real images, we place the camera on a robot arm so we can consistently take pictures with the same camera poses. Multiple images are taken from different angles and are manually labeled with a tool that allows to label multiple views at the same time. The data is then later imported in our synthetic data generator, so we can match the exact poses of the camera and objects in a virtual scene. To get accurate lighting, we use an omnidirectional camera to take multiple bracketed images and combine them into a single high dynamic range environment map. The result is a digital twin of the real images that can be used for researching the domain gap of training machine learning algorithms on synthetic data. The complete dataset consists of over 30,000 real images and over 500,000 synthetic images. All images are labeled and placed as specified in the Bob format. The dataset can be downloaded on the following link.
So the main drawback of our current approach is that we still need to manually assign appearance properties of the object at hand. For example, suppose we have a CAD model of a metal brick and some example images of how this brick should look like, we still need to search for realistic textures in the material database, or we need to generate them ourselves, as we do with the defects. Sadly, it is almost infeasible, or at least too labor intensive to exactly resemble the appearance of the real object. One can argue that the variations in material appearance are not photorealistically enough. Instead of manually assigning these textures, wouldn't it be better to directly extract them from the physical examples? To tackle this problem, we are building an appearance variation scanner. The idea is that we can put any tabletop physical example on the scanner and that the output is a realistic material representation of that type of object. This is achieved by projecting different types of patterns using an all-LED illuminator. Here you see our prototype of the scanner at work. Each turn, a different illumination pattern is captured with a camera. The different patterns are shown here. The idea is that with this approach we can extract texture properties that can be used to generate any kind of new variations of material properties.